Before we formally introduce the idea of the electric field, I first want to spend some time discussing fields themselves. A field is an idea from mathematics that can loosely be described as a type of quantity that has a value at every location. Some of the quantities we encounter in physics and our other science courses are fields, while other quantities we work with are not fields. At this point, I'm going to say, pause the video and see if you could think of an example of a field. In other words, see if you could think of some example of a quantity that you're familiar with that has a value at every location. A common example of a field that we're all familiar with is temperature. At any location, I can assign a value to the temperature at that location. Therefore, temperature is a field. Now, because we live in 3D space, temperature will be a field that takes on a value at every location in that 3D space, and that can be challenging to draw, but that's an artistic challenge. Because this quantity has a value at every location, temperature is a proper field. As an aside, another way I could kind of think about temperature being a field is I could think of temperature as a function of position. Given any position x, y, and z, you could plug that in and get the value for temperature out. Now, in practice, this would be an incredibly challenging problem to work with because certainly the form of this function would be very complicated. But you could still imagine, given any position, you get a value out for temperature. Therefore, temperature is a field. Now, last semester, we talked about scalar quantities versus vector quantities. A scalar quantity is a type of quantity that only has a magnitude, while a vector quantity could be thought of as a type of quantity that has both a magnitude and a direction associated with it. Temperature was given as an example of a scalar quantity. To fully know the temperature at a location, you only need a single piece of information. You just need the value of the temperature. Now, it is true that temperature can change from one location to another if you're in a hotter region or a cooler region, but regardless, the temperature at a specific location is fully described with just a single number. There's no such thing as direction of temperature. That's a meaningless statement. Because temperature is a field, because temperature has a value at every location, and because temperature is a scalar quantity, you only need a single number to describe temperature at a specific location, we could say that temperature is an example of a scalar field. In addition to scalar fields, there is also the notion of a vector field. A vector field is a field that possesses both a magnitude and a direction at every location. Pause the video and see if you could think of an example of a quantity that is a vector field. One common example of a vector field is wind velocity. The magnitude of the wind velocity would be the wind speed, how fast the wind is blowing, and the direction of the wind would be the direction of the wind velocity vector. Because everywhere in the atmosphere, I could assign both the wind speed and wind direction, I could say wind velocity is an example of a vector field. To motivate the idea of the electric field, I first want to recall what we talked about when we were discussing Newtonian gravity in 121. Remember Newtonian gravity? We have the force of gravity is G times m1 times m2 over r squared, and we know that gravity is an attractive force. So if I place an object here, we'll say this object has mass little m, and the mass of the Earth is me. I would say that the object feels a gravitational force. The strength of the gravitational force is G times little m times the mass of the Earth divided by the distance between the Earth and the little object squared. And the direction of the force on this object is going to be towards the Earth. That's because we learned gravity is always attractive. If I want to, I could take this force of gravity equation and rearrange the terms so it looks something like this. Now, it might not be obvious right now, why would we do this? And I'm going to say we're not changing anything fundamentally. These changes are just cosmetic. We are only changing the order of multiplication. We're adding some parentheses. But it turns out there will be a useful reason why we might want to look at the force of gravity on the small object in this manner. I could imagine that at every location in the universe, there is a well defined notion of distance from the Earth. Maybe I'm really close to the Earth, then that distance will be small. Maybe I'm far away in a distant galaxy, then that distance will be really large. At every location in the universe, there is a notion of how far away from the Earth you are. Therefore, I could think of the quantity that I call distance from the Earth as a type of scalar field. And similarly, I could say the gravitational constant times the mass of the Earth divided by distance from the Earth squared, that is also going to be a scalar field, because no matter where in the universe you go, this quantity will always be well defined. We're assuming in this discussion that you're not allowed to be on Earth, you have to be somewhere else. Now, if you're close to the Earth, the value of this field gm over r squared is going to be large because 1 over r squared is going to be a large number. If you are very far away from the Earth, r squared will be huge, so gm over r squared will be a small quantity. But nevertheless, the quantity g times the mass of the Earth divided by r squared is still a well-defined idea at every location. Also, everywhere in the universe, there is a notion of the direction towards the Earth. If you move to a different location, that direction might change, but that direction still exists everywhere in the universe. So I could say the numerical value gm over r squared combined with the direction towards the Earth is a proper vector field. It has both a magnitude and a direction. Now, it is true the Earth orbits the sun goes around the Milky Way galaxy, the Milky Way is moving through the local group, which is part of the Laniakea supercluster, and all these objects are in motion. But this just means the notion of distance to the Earth and direction towards the Earth might change. But nevertheless, at any given instant, these are still meaningful concepts. So these are still a proper vector field. The direction towards the Earth exists, and the combination of gm over r squared with direction towards the Earth does make for a vector field. So why is this going to be useful? Well, let's say I place object A right here. So object A has mass ma and a distance rea away from the center of the Earth, so there will be a force of gravity on object A given something like that. I could place object B over here. Object B has mass mb, has a force of gravity looking something like this. It's a distance reb away from the center of the Earth. I could generalize this idea. I could say the force of gravity on any object, no matter where it is in the universe, due to the Earth, could be written as the mass of that object times g times me over r squared, and the direction of that force is going to be towards the Earth. The usefulness of thinking about the gravitational force on an object in this form is we could now write the force of gravity on an object is equal to the mass of that object multiplied by the gravitational field from the Earth at that object's location. Let's think about what this equation, which is written in words, really means. First of all, I'd like to point out that force of gravity on the left-hand side of the equal sign is a vector quantity. The mass of the particle is a scalar quantity, and the gravitational field at that particle's location is a vector quantity. Because mass is an inherently positive quantity, then the force of gravity is always going to be in the same direction as the gravitational field at that particle's location. This is the same idea as force and acceleration are always going to be in the same direction from F equals ma, because mass is an inherently positive quantity. Secondly, I would like to point out, when I look at this equation, if I'm looking at the right-hand side, I see mass of the particle and I imagine that, okay, there is a particle and that particle's mass is a property that is inherent to the particle. Then I look at the second term, the gravitational field at that particle's location. When I see that, I am thinking the Earth sets up that gravitational field. The strength of the gravitational field is the mass of the Earth divided by the distance from the Earth squared. Both of those two terms I just mentioned are in relation to the Earth, and then multiplied by Newton's gravitational constant. It's only a constant, so I could associate it with the mass of the Earth over r squared. Also, the direction of the gravitational field is pointed towards the Earth. At every location in the universe, there is a notion of towards the Earth and gme over r squared. So I imagine that whether or not this other particle exists, if the Earth exists, this gravitational field will exist at every location. So I can now generalize the strength of the gravitational force as being the mass of a particle multiplied by this field that exists on account of the Earth existing. So the gravitational force on the particle is a result of the Earth creating or setting up this field at every location in the universe.